Chapter 8, Part 2. What we discussed earlier, some reactions of alkenes where we are able to make alcohols out of several methods following Markovnikov versus anti-Markovnikov addition. We also seen how we could do hydrohalogenation of alkenes, same exact way, whether we follow Markovnikov or anti-Markovnikov. Today, we're going to be continuing on the electrophilic addition reactions to alkenes. One of those reactions is halogenation reaction. In this reaction, you're always going to react an alkene with an Cl2, Br2, or I2, and end up having an anti-vicinal dihalide. What does that mean? Vicinal dihalide. Vicinal dihalide means you have two halides sitting on two adjacent carbons. And when I say anti, it means the two halides are on the opposite faces of each other. And that could only be explained when we look at the mechanism. So if I would have a Br2 or Cl2 or I2 react with any other nucleophile than alkene, we will always see that the nucleophile will grab one of the Br or the Cl and kick off the other. But in the case of the alkene, it's an interesting scenario that the alkene is going to actually have the reaction with one of the Br, well, it's going to be basically polarized enough to kick off the second, and it doesn't just do an addition. Rather, it's going to actually be forming what we call a three-member ring, bromonium ion, or chloronium ion, or iodonium ion, in the case of using Cl2 or I2. So this is the intermediate that we're going to see in the mechanism. So the very first step, always going to be the alkene being the nucleophile and the halogen to be the electrophile, never the other way around. So that pi bond will attack one of the halides, kicking off the second, and that halide is not going to be bonded to one carbon of those alkene carbons. It's going to be bonded to two. So that's why you end up having a three-member ring. That's a protonated halonium ion, and this halonium ion will be basically having that halide on one face or the other, so pointing up or down. And once you have that formed, the other halide will come and attack from the opposite face of where the bridged halide is. So if this is pointing up, the existing halide in the three-member ring, if it's pointing up, that means the halide has to come from the back, and vice versa. If that is pointing away, then the halide has to come from the front. So you end up making the anti-addition product. So that will be the vicinal anti-dihalide. Here's another example. We could see basically the cyclopentene reacting with Br2, so you end up making the bromonium intermediate. And once you form that bromonium intermediate that's pointing down, the bromide will come from the opposite side. So that's why you end up making the trans dihalide. So that's important to keep in mind, the anti-stereochemistry addition here. There is no mentioning of Markovnikov or anti-Markovnikov due to the fact that you have the electrophile being symmetrical. So it doesn't matter which one goes which. So here is a stereospecificity example. We could see that when you have a cis alkene to start with, that configuration is retained in the product. So when I have the two methyl groups being cis in the alkene, we're also going to notice that they are cis in the final structure as well. So the way how I would do this is basically having the two halide being anti, and that will keep the two methyl group the way how they started to be on the alkene structure. And that's what you see here. You have a cis dimethyl and you have the two bromide being anti. So this basically, and the other. What's the other? Where the two methyl groups being away from you. So if I want to draw the 3D of the second structure, which is the enantiomer of it, I will just draw the same exact one, but switch the two methyl group to be dashed, bonded to those two carbons. If I start with a trans alkene, I'm going to end up making basically the trans dihalide, definitely, and the two methyl groups will be basically anti as well. But keep in mind, as we learned in chapter 3, the rotation of the sp3 bond allows the two carbons to rotate around each other. So if I rotate this carbon around the second, that will generate a conformer where the Br is pointing on the same face and the methyl will be up. So if I rotate this to having the Br on the same face of the second Br and the methyl to be basically a wet bonded methyl, then I mean that basically having a structure that does have plane of symmetry. Therefore, you will end up having a meso compound. You cannot present the enantiomer of it and calling it is the enantiomer, because that enantiomer is an identical compound of the first. And once again, that only happens when you have a transalkene that is symmetrical. So if in the case of having diphenyl, if in the case of having basically two groups of the same being transalkene, through halogenation, you will always end up having the meso dihalide. That's important to keep in mind. The bromine test is considered to be a qualitative test. So if I have an unknown and I am suspecting if it does have an alkene or not, what do? I mix it with Br2. Br2 as a liquid, it's a brown colored liquid, or sometimes actually you see it deep red. So that colored liquid, if you mix it with alkene and that test tube had the color disappear, that means I have a double bond that consumed the Br2. But if I have that unknown mixed with Br2, which is once again brown or red colored solution, and it stayed that color and it didn't disappear, that means I do not have an alkene. So the presence of the alkene will always be basically tested using a bromine test. And not necessarily a single alkene, could be multiple alkenes, and you will also have those alkenes being brominated. This test is not being used as a synthesis method. We use it as a qualitative analysis method. That's the first mechanism. So the halogenation of alkenes, it's a required mechanism. The second mechanism, which is very similar to the first, is the formation of halohydrin. So in the halogenation, we added Cl2 or Br2 or I2, and we ended up making an anti-vicinal dihalide. What happens if I add water with the halogen? So ending up basically a X2 being a Cl2, Br2, or I2, and have the solvent being water. Well, I'm going to end up making not vicinal dihalide. I will end up making basically a halohydrin. What is that supposed to mean? Halohydrin means you have a halogen and a hydroxyl group. So chlorohydrin in the case of Cl2 and water, bromohydrin if you have a Br2 and water, iodohydrin if you have I2 and water. The mechanism is very similar. So it is a Markovnikov addition, meaning your OH will end up attacking the more substituted carbon. So you will be making halonium ion, the bridge, the three-member ring that we've seen in the halogenation mechanism. And once that halonium ion is formed, the water molecule will attack the more substituted carbon. So your halogen will stay on the less substituted carbon. And here's the detailed mechanism. So if I have alkene mixed with halogen and water, do not interfere with the water. The alkene will actually attack the halogen first, just like how we've seen it in the halogenation mechanism. So the one of the halogens will basically interact with both carbons of the alkene, and that will form the halonium ion, kick off the X minus. Once you make that halonium ion, whether it's bromonium or iodonium or chloronium, water will attack from the opposite side of the bridged halide, and it attacks the more substituted carbon. That's important to keep in mind. If the two carbons are equally substituted, then it doesn't matter which one you pick to attack it with water. Once that's giving me the protonated halohydrin, another water molecule will come and pick up that hydrogen to give you the neutral halohydrin. It's a Markovnikov addition due to the fact that you're going to be adding the OH to the more substituted carbon. So indicating that it's going to be the more electropositive carbon. Here's an example of cyclopentene reacting with Br2 and H2O. So you're going to end up having basically the Br added first. So if it's pointing up, the OH will be pointing down. And the enantiomer. The enantiomer meaning Br pointing away, OH being pointing towards. So it's an anti-addition product, and there is no carbocation formation. It's a halonium ion intermediate. And that halonium ion intermediate is the justification why you get the anti-addition product. And you could see here clearly when you have the Cl basically pointing in that halonium ion, that the carbon that's more substituted is going to be more electropositive, and it's going to be the one that's going to be attacked by water. So that's a very important thing to keep in mind. Every single time you have a halohydrogen formation and you have an unsymmetrical alkene, pick the carbon that's more substituted to be the one that's going to carry the OH, and the other one to be attached to the halide. Here's some more examples. If I have a methyl, 1-methyl cyclopentene, Br will end up basically being on the less substituted, as you see here, and the OH will end up being on the more substituted, as you see there, and they are anti. So you're going to end up basically making OH up, Br down, or the other way around as well. So both enantiomers, there is no certain percentages. You may end up having 50-50 of those two structures or those two enantiomers. So you have OH pointing away and the Br pointing towards being the second structure. So whether you draw both of them, when you are asked a question on a quiz or an exam, you draw both of them, or you draw one of them and say plus enantiomer. That's perfectly fine. Here's some more. So you could see that when you have the Br2 added to that cyclohexene, giving you the bromonium ion, whether you react to Cl- or H2O, you end up basically making the anti-addition product. That's important to keep in mind, plus the enantiomer. So that's the second required reaction when it comes to its mechanism. The third reaction, there is no mechanism for it, which is the catalytic hydrogenation of alkenes. We've seen this reaction previously when we studied the stability of alkenes. We said hydrogenation of alkenes, it's an exothermic reaction. And the way how we were using the heat of hydrogenation is by measuring how much energy the hydrogenation of an alkene releases. The more energy is released, the more indicative that the alkene is unstable. So the tetra-substituted alkene will give me the least amount of energy compared to the tri-substituted, compared to the di-substituted, starting with the trans being the most stable, then the germinal di-substituted, then the cis di-substituted. Mono-substituted will be less stable, meaning it releases much more energy than the other ones. And the ethylene will be the least possible alkene stable structure. So this catalytic hydrogenation, when we say catalytic, that means I have to have a catalyst. The catalyst basically can be a platinum, palladium, or nickel. So when you add the two hydrogens, it will be added syn. So the requirement here is to add the two hydrogens on the same face, whether up or down. So you may end up actually having two enantiomers. Make sure that before you label the second one to be an enantiomer, that there is no plane of symmetry. Because if there is a plane of symmetry, then obviously you are not forming a couple enantiomers. So you could see here clearly that if I have this structure, which is but2-ene, reacting with H2, you're going to end up making a butane. So there's no chirality here at all. Here is basically deuterium containing compound to prove that the two hydrogens are added syn. So the two deuterium attached basically on the same face, you could prove that the two hydrogens now, once they are added, they could actually form the one that's up or down. The two structures are not enantiomers due to the fact that there is a plane of symmetry here. So the syn stereochemistry is important to keep in mind when you do catalytic hydrogenation of alkenes. That's different from the halohydrin formation and the halogenation. These other two reactions, they are actually anti-stereochemistry when it comes to their outcome. Wilkinson's catalyst, usually when you mix platinum, palladium, or nickel, these catalysts, they tend to be heterogeneous. So if there is a system that I would like to have that catalyst to be a homogeneous catalyst, I will be thinking of the Wilkinson's catalyst. Nowadays, actually, there is other versions of the same catalyst. There is some hydrogenation will require the homogeneity of the medium in order for the hydrogenation to give me a good result. So that's just another catalyst that can be actually used in the hydrogenation. Now, whether you do homogeneous or heterogeneous, both are acceptable. It all depends on what are you actually hydrogenating. You may end up having a biological system compound that requires to have the hydrogens to be added on certain phase, not the other. So here's an example. So you could see that the DOPA S minus, where the hydrogen is pointing away, requires the two hydrogens to be added on a certain phase, which is away, not the other one. So having this hydrogen to be towards, it may end up actually having a biological inactive compound. So that's important to keep in mind, because the hydrogenation, how it works, whether you use a catalyst that is attached to a ligand, what we mean by that is having basically a ligand attached to the catalyst that will force the orientation of the hydrogen to be on one side over the other. So once the catalyst chelates to the alkene, it blocks one side, and it allows the second phase to basically be exposed to the two hydrogens, and the two hydrogens will be added on the same phase. Whether you use homogeneous or heterogeneous, you will always get the two hydrogens added on the same phase. So think of the catalyst as being basically a support that will have the two hydrogens attached and the alkene as well. And once that happens, if the catalyst has a ligand, the ligand will block one phase, allows the hydrogen to add into the second phase. Now, somebody might ask, okay, which of the two phases will be blocked? Depending on the ligand. Some ligands will be chosen because they're going to block the back because of their stereochemistry, and some ligands will block the front, allow the hydrogens to be added from the back. So whichever the desired hydrogenation product I'm interested in, I will base that on in my decision when I choose the ligand. So that clearly tells me basically how the syn stereochemistry in catalytic hydrogenation take place. So once again, catalytic hydrogenation, there is no mechanism to be required. So just be aware of the syn stereochemistry when you add the two hydrogens. The next reaction, it's addition of carbenes. Carbene is when you have a carbon, 2 bonds, and 2 electrons available. So you have total 4 valence electrons that doesn't allow it to carry a plus charge or a negative charge or a radical. So when you have this carbene, and there are 3 methods how to generate that carbene, know that the outcome will always be a cyclopropane containing compound, meaning this set of this set of carbons of the alkene will both bond to that carbon of the cyclopropane of the carbene. So you end up basically making once again a cyclopropane containing compound. There are 3 methods. No mechanism is required. You are required to know the set of conditions. The first one, it could be diazomethane, which is CH3N2. Diazo refers to the 2 nitrogens. CH3 refers to it to be a methane. So that's where diazomethane comes from. The Simmons-Smith, which is basically the CH2I2 mixed with zinc copper. And that will give me basically an intermediate, as we're going to see, CH2 zinc I, and I will show you that in a minute. And the third method, how to insert a carbene, and that will be different from the other 2 due to the fact that there are 3 halides on the haloform. 2 of them will stay on the carbon that's going to be attached to the 2 carbons of the alkene. So you're going to end up making dihalide cyclopropane. So that's important to keep in mind. So haloform, whether it's a chloroform or bromoform or iodoform, it doesn't matter. You're going to have NaOH and water along with the haloform. So that's important. So the alpha elimination, Simmons-Smith, or the diazomethane, these are the conditions that I'm going to be in need to insert a carbene into an alkene. So that's important to keep in mind. There is, of course, a drawback for the diazomethane method. That is, it's an extremely toxic and explosive, and the carbene can actually insert into the CH bond. So it's not a regioselective method. It does give you actually the alkene carbene reaction to be the major outcome, but you cannot prevent the other side product that may end up being formed because of the CH reacting with the carbene. So how does this diazomethane occur? Well, the diazomethane, which is CH3, as I see in here, so it's CH3N2. So this diazomethane, which is the resonance form, has a CH2N. So that does have another resonance form for it, which is the one that's negatively charged. That negatively charged, or the other, once it gets the nitrogen gas release in presence of heat or UV light, you end up making a carbene. So think of it this way, that this carbon now has a negative charge, but once you take that bond away with the nitrogen that's attached to it, it's going to basically get it back to four valence electrons around it. So that carbene, once it's formed, now it's going to react with the alkene to give you basically the cyclopropane. Now, diazomethane, there is also a second method, that's a Simmons-Smith reaction, which is the consists of CH2I2 and zinc copper. This gives me the carbenoid, which is the ICH2 zinc I. So the copper is there just to activate the zinc. It's not there to react with the carbene intermediate. So this step gives me the reagent that's required for the cyclopropane formation. So this alkene, once it sees the ICH2 zinc I, you end up basically making a cyclopropane containing compound. So whether I use the diazomethane or the Simmons-Smith condition, I'm going to end up having the same exact structure. Keep in mind, stereochemistry in the reactant has to be retained. So if I have, as we've seen here, if I have a trans or a cis, I will also see the cyclopropane containing compound reflects that stereochemistry. The third method, alpha elimination reaction, which is the use of haloform. So in this case is bromoform, CHBr3, and the base, and water. Water is basically being the solvent. So what is the hydroxide going to do? Hydroxide is going to deprotonate the bromoform, and that's going to give me the anion. And this anion will basically have one of the halides being kicked off to form a KBr. So that's an ionic compound. That's the motive for this step to happen. And once that happens, you're going to end up making the dibromocarbene. So if I have a chloroform, I'm going to end up having the dichlorocarbene, or iodoform, I'm going to end up having the diiodocarbene. This will be the one that's going to react with the alkene to give you not the cyclopropane containing compound only, but the two halides still attached to that carbon of the carbene. So you can see here clearly the 2-phenyl being trans, reacting with CH-Cl3 and aqueous hydroxide is going to end up making the cyclopropane moiety, and the 2 Cls still attached. So that's important to keep in mind. And the 2 phenols being trans as originally how they were oriented in the reactant. While the 2 ethyl groups are cis, the alpha elimination condition, which is bromoform and aqueous NaOH, you could see it clearly that the cyclopropane is added and keeping the 2 ethyl group being cis. So the 2 halides are attached due to the fact that the carbene, once again, it's gonna be having that those 2 halides attached prior to the alkene attacking the carbene. So that's important to keep in mind. So here's some more examples. You can see the difference between the two. So if I have a cyclohexene reacting with the Simmons-Smith condition, I'm going to end up making a cyclopropane fused to the 2 carbons that are the alkene carbons. If I have a haloform or alpha elimination reaction, I'm going to end up making a dibromo cyclopropane fused to the structure. So we have the required mechanism so far. You have the halogenation and the haloform formation. The next required mechanism is epoxidation. What does epoxidation mean? First of all, what's an epoxide? Epoxide is a cyclic ether. So when I look at this compound right here, I could see it's a three-member ring, and the two carbons are actually the original alkene two carbons, and the oxygen is coming from a peroxy acid. Peroxy acid moiety, it means that you have a carboxylic acid with an additional oxygen inserted between the carbonyl and the OH. So this terminal oxygen in the peroxy acid is the one that's going to be actually the source of that epoxide oxygen. And the other product will be that carboxylic acid. The mechanism is required. So it's a transition state containing mechanism, meaning it's a concerted mechanism. So there are several steps going to happen at the same time. So once you have the peroxy acid, it's going to be oriented in a way where the terminal oxygen will be the one that's going to be exposed to the alkene. And the very first thing is going to happen is that alkene is going to attack the oxygen, that terminal oxygen. That's going to push the other bond to go form a double bond. And the double bonded CO will be grabbing the hydrogen to end up basically making a carboxylic acid and an epoxide. So you can see here the transition state where partially broken pi bond, partially formed sigma bond with oxygen, and another partially sigma bond formed with the other carbon of the alkene, and partially broken bond with the oxygen, and so on. So you can see here the partially formed and partially broken bonds all in the transition state. The difference between a transition state and an intermediate transition state is being speculated what it looks like. There is no isolated intermediate. There is no isolated structure that we can call it a transition state. It has to be called transition state when we don't have an isolated compound from a certain reaction. So this epoxide will also be giving you basically stereochemistry defined. So if I have alkene with cis or trans, that will also be retained in the epoxide structure. So that's important to keep in mind. The next point is that the oxygen, just like the other reactions, the oxygen will be added on top or on the bottom. So you may end up actually having both structures being actually formed if they are enantiomers. So we could see here clearly that we have a cis alkene, meta-chloro-peroxy benzoic acid, meta-chloro-peroxy benzoic acid. That's another peroxy acid. So there are three peroxy acids that we're going to actually see in this chapter. All of them are epoxidation agents. So cis will end up staying cis, and you could see the oxygen basically being oriented up or down. It doesn't matter that you draw either of the two due to the fact that it's going to be meso. So do not draw the second and calling it enantiomer because of the plane of symmetry. While the trans will end up making basically the trans epoxide, and that will generate the other one as well, which is where the methyl groups are opposite to each other, but in the opposite faces. So methyl is down on this side and methyl is up on the other side. There's no plane of symmetry here, therefore you will have a racemic mixture of the two. So just to show you the other peroxy acids, so you have the peroxybenzoic acid. The other one we've seen is the meta-chloro-peroxybenzoic acid. So there is an additional chloro sitting on the phenyl. If there is no chloro, that will be the peroxybenzoic acid. The peroxyacetic acid. So these are the three peroxy acids that are possible to be used in epoxidation of an alkene. Now, once we make the epoxide, it gives us access to another useful product. What is that? Well, if I react an epoxide with H3O+, the very first step is going to be the protonation of the epoxide. So you're going to end up having a protonated epoxide plus water. This water will attack the more substituted carbon from the opposite face of the epoxide face. So if the epoxide is pointing up or down in this case, OH or water is going to attack from the front. So you're going to end up making basically a trans protonated diol at the moment. Once another water molecule grabs that hydrogen, you end up making a trans diol. So if I have an alkene and I'm asked to form a trans diol, I will be required to go through two steps. Step number one would be the epoxidation using peroxybenzoic acid or peroxyacetic acid or meta-chloro-peroxybenzoic acid, MCPPA. Then a second step would be H3O plus, and I have to indicate the numerical here, that number 1 step, number 2 step. So that's important to keep in mind. And you're always going to get the anti-diol. The trans diol will be the product out of the 2 steps, epoxidation followed by H3O plus. So you can see here clearly other examples. So the cyclopentene will end up making an epoxide product. If I treat it with H3O plus, I will end up making basically acetic acid being a solvent here. So H3O plus is being added. So you could think of it as basically the acetic acid is there just as a solvent. Once that happens, so you have the OH basically attaching the other side of the existing oxygen. So you're going to end up having a diol. There's no plane of symmetry here, so you're going to end up making the enantiomer as well. Here's a trans alkene. So MCPPA, you will end up basically making an epoxide. But if I have peroxyacetic acid followed by H3O plus, I will end up making a trans diol. So that's the difference between having H3O plus or not having H3O plus with the peroxy acid. So if I don't have an H3O plus, I will end up making the epoxide. If I have H3O plus, I will end up making the diol. Both mechanisms are required, epoxidation and the formation of the diol. So it's very important to keep in mind how we make the epoxide and how we make the trans diol. What if my interest is to make a syn diol? What is that supposed to mean? Cis diol. So syn dihydroxylation, syn dihydroxylation, it means that you are inserting 2 OHs on 2 adjacent carbons. So you're going to end up basically making a vicinal diol. So how does this happen? Well, I will be required to go through one of the 2 steps. Either osmium tetroxide with a co-oxidant, that's a hydrogen peroxide, or the use of diluted basic KMNO4. Diluted basic condition of KMNO4. Either of the 2 will generate the diol. Now, the osmium is the toxicity of it. The KMNO4 is the yield of it. So each of the 2 methods have drawbacks. But again, these are the 2 ways how we can make a diol out of an alkene. It's very important to keep in mind that it's going to be a syn diol. There's no mechanism required for either of the 2. So whether you make the osmate ester or the manganate ester, you're going to end up making basically the 2 OHs coming from the oxidizing agent. Whether it's an osmium tetroxide or a KMNO4, calcium permanganate, the 2 oxygens are coming from there. So the role of the hydroxide in the KMNO4 mechanism is going to basically to do the hydrolysis of the manganate ester to end up making the diol. So that's important to keep in mind. And of course, the indicator that the reaction did work is that the formation of the brown precipitate of the manganese dioxide. So whether you, once again, whether you use osmium tetroxide, hydrogen peroxide, or basic diluted KMNO4, either of the 2 will generate the syn diol. Keep in mind that the syn diol is different from the trans diol. That the trans diol, I'm going to have to go through the epoxidation step first. And once I make that epoxide, then I will treat it with H3O+. Now, the KMNO4, the reason why I say it's diluted, because if it's a concentrated KMNO4, what's going to end up happening, once you form that diol, you're going to end up actually pushing that to go through what we call an oxidative cleavage. What does oxidative cleavage mean? If I have a basic condition, KMNO4, that is concentrated KMNO4, and you could see here warm, so heat might actually push it even more, that it's not gonna stop at the diol step. It's gonna actually push it to form 2 carbonyl structures. So think of it this way, that the C double bond C is gonna be broken and it's gonna be oxidized. So the C double bond C is gonna end up making 2 C double bond O. So this side will end up making basically the acid due to the fact that there is a hydrogen there, And once you have the aldehyde is known to be further oxidized to the corresponding carboxylic acid. And if I make the ketone will stop at the step of the ketone. So here's the difference between an alkene that does have a side of it that does have a hydrogen and an alkene that doesn't. If you have an alkene reacting with concentrated KMnO4 and hot, that means I'm going to be breaking that double bond into 2C double bond O, and the one on the left will become the cyclohexanone, which is the ketone, and the one on the right, it will give me the aldehyde first, which will be further oxidized to the carboxylic acid. So that's what's going to happen in the presence of a concentrated KMnO4. So that's very important to keep in mind. Here's another example. You could see here that you have an alkene that's going to break into a single structure rather than two structures. So it's going to break this into two parts, C double bond O OH and a C double bond O OH. There is no loss or increase in number of carbons. So that's important to keep in mind, that what's going to happen is only oxidation, not extension of carbon chain. So that's important. So that's the difference between diluted basic KMnO4 and concentrated hot KMnO4. So one will give me the syndiol and the other one will give me the possibility of two carboxylic acids, or the possibility of having a ketone and another ketone, or the possibility of having a ketone and a carboxylic acid. So the opposite to this, which is milder than concentrated KMnO4, that is also an oxidative cleavage reaction, is ozonolysis. What does ozonolysis mean? You're using ozone, O3, followed by a workup step that could be zinc or dimethyl sulfide. So dimethyl sulfide or zinc are basically optional. Whichever of the two you use, you will end up making the same outcome. What's the difference between ozonolysis and concentrated KMnO4? Well, we just seen that if I have a side of the alkene in the presence of concentrated KMnO4 has a hydrogen, that's going to end up an aldehyde, and that aldehyde will be further oxidized to the carboxylic acid. Well, in the case of ozonolysis, it's not going to, that aldehyde will not be further oxidized. It will stop at the aldehyde step. So the milder condition, which is the ozonolysis, it doesn't have the powerful oxidation phenomena that will push the aldehyde to the carboxylic acid. So if I have an alkene that one of them has a hydrogen, I know that's going to, in the presence of O3 followed by zinc or dimethyl sulfide, is going to break to two double bonds that are carbonyl, and the side that has a hydrogen will stay as an aldehyde, and the side that doesn't will stay as a ketone. So that's important to keep in mind. So you could see basically the mechanism that's not required. It's going to give me basically an ozonide. You could look at it, but again, you are not required to know the mechanism of ozonolysis or the KMnO4 or the osmium tetroxide. If I have an alkene that's a cyclic, then obviously I'm going to end up making double bond cleaved, and I'm going to end up having a single structure that's going to be a dicarbonyl. So the top one will become a ketone, and the bottom one will become an aldehyde. So we could see it clearly that this, if that aldehyde, if it does have a concentrated KMnO4 in the condition, it's going to be taken further to the carboxylic acid. But if I have ozonolysis condition, it's going to end up staying as the aldehyde along with the top carbon being the carbonyl of a ketone. So that's important to keep in mind. The difference between concentrated KMnO4, warm, and ozonolysis condition. Both reactions are labeled oxidative cleavage of an alkene, but one will take the aldehyde further to the carboxylic acid, which is the KMnO4 one, and one will not take that aldehyde to carboxylic acid. We'll keep it as an aldehyde to be the final structure. Now, as I mentioned, in the case of concentrated KMnO4, if I have an alkene that's going through ozonolysis, I may end up having two ketones. I may end up having one aldehyde, one ketone. I may end up having two aldehydes. So it all depends on how substituted the alkene is. So here's an example. So basically, it's asking you, how would I make, or what would an alkene be that will give me access to those two structures. So thinking backward, so knowing that I have an aldehyde and a ketone, then I know that I'm going to need ozonolysis condition, not concentrated KMNO4. So whether I have basically the C double bond C there, so where the CH3, CH2, CH3, which is the other part of the molecule, or the other way around, having basically the trans of it. So whether you get the cis or the trans, you will end up making the same outcome. So that's important to keep in mind. How would I know it's ozonolysis, not KMNO4? Due to the fact that there is an aldehyde. If this would have been carboxylic acid, then I will be required to use concentrated KMNO4 with either of those two alkenes to end up having this outcome. Polymerization, it's a reading material, so you could basically go through this material to know what polymerization is about. There are three ways how to do it, whether you go through a cationic intermediate or a radical or an anionic. So it's all basically going to be reading material. You're not going to be asked a question in an exam or a quiz on this material. Olefin metathesis, though, it's an important reaction. No mechanism is required. However, olefin metathesis is talking about basically reacting two alkenes together. And those two alkenes, if they react together, they're going to switch partners. What is that supposed to mean? So if I have an alkene that's A attached versus the B attached one, I'm going to end up making basically a cleavage of the two double bonds and switching partners. So I'm going to end up making the cis and the trans. So we could see a real example. So the propylene, in the presence of a catalyst, there's Nobel Prize winner reactions actually that invented this reaction. So Grobs and Schrock. So you could see here, and there's a third French person. So that's actually a lot of effort been put into this chemistry to come up with this invention. So a catalyst will cause the olefin metathesis to basically break that double bond, and two of those reacting together to give you basically a butene, that's cis or trans, and ethylene. So think of it as basically a C double bond C that's going to break on both alkenes, and you're going to switch partners. So that's the cross metathesis or the olefin metathesis. And if you have the possibility of forming cis and trans, you will end up making both of them. So that's important to keep in mind. The same exact catalyst can also be used to get two alkenes together if you have the two alkenes in the same structure. So intramolecular metathesis or olefin metathesis, that's called actually ring closing metathesis, RCM. RCM, it's also olefin metathesis, but rather than splitting two alkenes to give you two different switching partners components, you will end up making actually a ring out of it. So that's the purpose of this reaction actually. So you will end up making a C double bond C that's going to break to give you CH2 with another CH2, and that's the ethylene. And you're going to end up making basically attaching that carbon that's internal with the other carbon that's also internal to end up making this member, this cyclic alkene structure. So that's important to keep in mind. Some of these reactions also that actually have an alkene, once it's going through the same catalyst that's being used for olefin metathesis to break that double bond, and it end up being polymerized. So repetitive unit of the same that will be basically through a reaction that's called ROMP. What's ROMP? Ring opening metathesis polymerization. So there is a lot of chemistry taking place just under the topic of metathesis. So whether it's reacting two alkenes together to basically switch partners, or putting two alkenes together to make a ring, or breaking up a double bond to be able to polymerize that unit, that's actually a lot of aspects of the same chemistry that's taking place through a catalyst that's being used. And the idea behind this catalyst is to basically the transition metal will chelate to one alkene and then activates the second to put them together. And it's always going to be the internal carbons of those alkenes that's going to be actually attached to each other, and the terminal ones to be giving you the second product. And this is a very important reaction. No required mechanism. So keep in mind what is this reaction about, and how would you basically predict a product if you are given any of these examples in an exam or a quiz. And that's the story of chapter 8.